No, not between the two.
Well, Lionel says nobody has a clue. Freddy says they are the same. What's going on? I mean, both of these guys are computing scatter matrices.
Imagine Freddy knows something I don't.
But yeah, which means that probably means that it's probably right.
So welcome everybody for the final afternoon session of this marvelous Joao Catano. All listening.
Okay. So I'm going to talk about the most recent developments on the OP for scattering amplitudes in planar angles before. So this is work that was done in collaboration with Anthony and Vasco, see about plugins that have been here, and they are galaxies that were Benjamin that went yesterday. Yeah, part of my talk on these papers. All right, so the story starts with this moment between scattering amplitudes and Wilson rules that was 2007. And here the statement is, suppose we want to compute some scattering amplitude, so we prepare some states of the theory to scatter these particles with some given external momentum. And then the idea is that you pick these vectors and you concatenate one after another, forming some closed polygon. And the statement of this duality is that if you complete the expectation on this contour, expectation of our rules on this contour, you usually get this. So this was proposed in 2007 by several groups, both at and basically this maps you some four-dimensional observable into another four-dimensional observable. But this is not enough if we want to use integrability. Integrability appears when you find some sort of auxiliary two-dimensional problem. And that appeared, such a proposal appeared in 2010 by these four guys, where the idea would be to look at some polygon Wilson loop to non-intersecting line. And then you imagine that these non-intersecting lines would represent a system of white and empty part, moving at speed of light, and there's some flux tube between them. And you would imagine that this flux tube would be greater than the bottom of the polygon, so propagating to the top, where it would be annihilated. And basically the statement is that the expectation value of the Wilson loop is summing over all excited states that can propagate during the middle. So what is nice about this is that this flux tube is intrinsically a two-dimensional object, so it can be described by, for instance, spin chain states, or as stronger by some two-dimensional world sheet. And so it's the perfect arena to apply interoperability techniques. So later, there was a refinement of this idea, which was by the name of Pentagon V program, or Pentagon Product Expansion, so Pentagon V or both for short. And here you break more the rules. You follow more carefully the evolution of the state inside the polygon. So imagine you have a polygon. Okay, so in this case it's an hexagon. What they propose to be to break this polygon into smaller building blocks. So, and there's a canonical way of doing that. So suppose you pick some cusp of this polygon and you draw some line that intersects the polygon in another edge of the other side. Okay? So this defines for you a square. Okay? And you will do that successively. So you go to the next cusp, you do the same. And the final cusp, you do the same. So this is a canonical way of breaking the polygon into a sequence of squares. Now, two squares together form a pentagon. So here you have one pentagon, another pentagon, and another pentagon. First, in each square, you have some flux tube state propagating. So it starts with some vacuum that will be excited into another state because of the cusp. So you have some psi 1, then you have some psi 2 in the other square, and finally it's interrelated into the vacuum. Okay. So the is to sum over all these states that propagate here in the beginning. So there's two pieces here. There is propagation in a given square. Charges, corresponding charges of all the states. So this state has some energy, some momentum, some angular momentum. Okay. And then you have, some pentagon transitions. Basically, goes to the dynamics of this transition between vacuum to psi 1, psi 1 to psi 2, and psi 2 to the vacuum again. All right. So this is nice because this is valid at any coupling, but the thing is that if you want to compute this expectation of this will all you need to know is the associated towards the square. So you need to know the spectrum of the flux in states, which was well studied by Graham in 2000. We know this at loops, and also there's also the using interoperability techniques in 2013 and then in several other papers later. Let me just mention that you might be asking where's the problem, where's the external moment encoded in these coordinates, how sigma and phi, and that kind of. But for instance, the pentagon transitions are just encoding the dynamics of the problem. They don't care at all the kinematics. So why is this tau sigma and phi encoding the kinematics of the external momentum? So the first thing you have to realize is that this is a conformal invariant problem, so it should become, the final result should become as a function of the cross ratio. And how does the cross ratios come about? Associated to symmetries of these middle squares. So suppose you have a square. Okay. So a square breaks some of the conformal symmetry of the problem, but it preserves three of them. It preserves symmetry that moves points in the vertical lines, preserving these horizontal lines, and this vertical direction is what I call the tau. Then it also there's another symmetry that preserves the two horizontal lines, that moves points around the two horizontal lines, but preserves the two vertical lines. And this is the direction that I'm referring to as pi sigma. And because we're talking about the whole square, we can put the whole square in a two-plane. So you have transverse directions that you can rotate. And this is fine. Now, we mentioned this square is embedded in a larger volume. So let's consider that this square is it's part of an hexagon, for instance. Now, the idea is that if you pick the symmetries that preserve, or the generators that preserve this square and you act with them, let's say on the bottom test, we'll move these points, generate a family of polygons, or hexagons in this case, that are three coordinates. But 3 is precisely the number of independent conformal cross ratios of an hexagon. So you can actually parameterize these cross ratios using these three coordinates. And here is an example of how to map between one and another. And this pattern is general. So if you go to a larger polygon, an n-sided polygon, you will have n-5 middle squares. In each middle square you have three coordinates, so you have 3 times n-5 parameters, and this matches precisely with the number of independent formal cross ratios in the problem. So that's a good parameterization. Okay, so this is a brief review of the original OPE approach. Now, what I'm going to talk in the rest of the talk is going to be mostly on how to generalize these for superamplitudes. Okay, so a superamplitude, probably you're familiar with this expansion. So you start with some MHV, and then you have some polynomial of these auxiliary Grassmann variables that just will keep the kind of particles that you're scattering. So you have an expansion that starts with MHV, then NMHV, and square MHV, and so on and so forth. Okay. So this approach that the original OP approach was meant to solve the problem of MHV. So we now want to generalize it to take into account 2 other components. So another comment is that later there was a proposal of generalizing some Wilson loop, the Bosonic Wilson loop, into some sort of super Wilson loop that would be dual to this amplitude. And this super Wilson loop would have an expansion of this core. So you start with the Bosonic Wilson loop where you just integrate the H field, and then the other components you will integrate other fields other than just the H field. So, for instance, now these eta variables in this super Wilson loop business would have one R-charge index as usual, but the other index would correspond to would label basically the edges of this null polygon. And the intuition, so we don't care much about the results, they are not very relevant for us, but more or less the intuition is if you pick one component, say W1114, this would be some NMHV component. 1114 means that you put 3 units of our charge in the H1, so that's roughly speaking inserting inside, and 1 unit of our charge in the H4, and that would be some insertion of some side R along this edge. But again, these details of how do we integrate precisely are not relevant, and this business is full of subtleties. But basically what we need is that this object exists, pretty much. Now, how can we be generalized to get us all this some sort of super vector? So you will start with so this would be the definition of some super pentagon, where the lowest component would be the Bosonic pentagon, and then you would expand with some sort of auxiliary Grassmann variables, very much in the same spirit as the beta variables, these bookkeeping Grassmann variables that we have seen, but with an important difference. Here, the chi variables are associated to a pentagon instead of an edge. So this poses immediately an apparent paradox, is that it seems that we have much less degrees of freedom, right? There's many more edges than pentagons. So for instance, in an hexagon has 2 pentagons, so you can distribute your charge in only 5 distinct ways. But we certainly have many more independent or many more components from the superamplitude. But the way out of this apparent paradox is that, in fact, not all components of a superamplitude are independent. They are, in fact, related by superamplitudes. And in fact, you only need 5 to describe the full NHV power components. And this pattern is more general. So there was this very nice paper in 2009 where they have computed, basically counted the number of independent components for an arbitrary polygon, for an arbitrary helicity, and it's counted precisely with the number of independent components from the superpentagon. So this was the sign that this program could work, and in fact this expansion in pentagon seems to be some sort of minimal basis that gets rid of all the redundancy coming from the supersymmetry. So it seems that this can work. So our proposal is that we we can expand our super amplitude or super Wilson loop in terms of these charge characters. So again, we start with a sequence of bosonic pentagons that describe the MHV. And then we have an expansion in these high variables. And you generate all the power of an MHV, amplitudes and square MHV, depending on, and you have all the components by distributing their charge among the different patterns. So we have two expansions, one and the usual expansion, and then we ask the natural question, what is the relation between the two? That's what we want. How do we map one of these components into another of these components? So this is equivalent to asking the question, how to charge a pentagon? How do we put, what does it mean to put a unit of our charge in a given pentagon? And to answer that question, to get an inspiration, we go back to the way we introduced the conformal plus ratios in the problem. So as I said before, the conformal plus ratios, according to IGST15, they are related to symmetries of a square. So basically, a square is a transition from one state to another state, from the bottom to a state from the top, which turns out to be the same because the propagation in the square is diagonal. But then what you do is you pick the symmetries of this square and you work with them on the state that is entering that given square. Okay? And that introduces the Gaussian finding problem. Now, for a pentagon, we also have from one state to another. And the idea here would be to find some charge, which has to be a supercharge, that preserves this pentagon. So in this way. So you have a pentagon transition, which is kind of some sort of form factor, and the goal would be to find some supercharge that commutes to this pentagon, and then this pentagon operator, and then we would act with this charge on the state that is entering the pentagon. Okay. So what charge should we use? So we have 16 parallel supercharge. Now let me mention that we cannot use just overall generators because they do not preserve the pentagon. So we have to really use some supercharge. So we have 16 parallel supercharge, and we can write them in this way using the twistor variables. And the statement about the variance under symmetry is written here. So what we do is, what we want is not to arrange some combination of these charges such that these three edges that define the pentagon are preserved. So you imagine that this pentagon is embedded on a larger volume. So you have some state coming in, some state coming out. So we want to preserve these three edges. And our proposal is the following. So this operator means inserting one unit of our charge in this pentagon. So what do we do? We pick this operator Ci in eta I, which is how a supercharge is defined. And then we contract with some co-twister that is precisely orthogonal to the twisters that define this pentagon, such that so it's orthogonal, so we preserve this. And then we sum, we have here sums, we sum over below this given pentagon. This summation is the equivalent of saying that we act with this charge on the state that is coming in. Okay, this state in the bottom of the pentagon. More mathematically, we can express one eta component in terms of a chi component very easily. Let me give you a specific example to show you how does this work in practice. So imagine you have some NMHV epsilon. Okay, you have three pentagons, and now let's suppose that we want to compute this particular component here. So we put 3 units of our charge in the second pentagon and 1 unit of our charge in the third pentagon. So we are instructed to apply this operator that I defined, and this, if you open up and use the previous map, this just gives you some complicated combination of supercomponent amplitudes with some coefficients. So now we want to test this, right? And how do we test it? So first, there is a lot of data for these super amplitude components that we cover. So we can compute perturb the right-hand side of this equation, come up with some integrability basic definition for a charged pentagon. So we have to compute this left-hand side by a different independent method. Okay? So that's what I'm saying here. So we are now going to compute this based on integrability, which we will be able to do at all loops. Then we expand the left-hand side and match with the right-hand side. In this way, we're testing if it's appropriately designed or not. Okay, so another comment is that, of course, as I said before, we can invert and this kind of compute one component of a superambiguity in terms of charge. So how do we compute charge pentagon from the integrability point of view? We do the following. So the basic idea is to use this observation from Model in 2007 that tells you that a supersymmetry generator is realized on the flux tube by inserting some fermion and take its momentum to be 0. So imagine you have some state, some flux tube state. We want to act with a charge on this supercharge on this flux tube state, and the statement their claim is that you might as well insert a fermion and take its momentum to be 0, or in terms of the rapidity, take its momentum to be infinity. Okay. So imagine we want to compute the transition of, let's say, the vacuum into a psi bar in a charged pentagon. Okay, we put here this symbol to denote that we have one unit of our charge in a given pentagon. So we use this idea. We start with the uncharged pentagon. We insert a fermion here, and it takes its momentum to be 0 or the rapidity to be infinite. If you do that, so the uncharged or the bosonic pentagons are already known. So you can pick their expression and take this limit. And what you find out is that the final result is, okay, so here there's a typo. So the charged pentagon is the uncharged one dressed by some simple function. And this is a general pattern. So if you want to compute uncharged, if you want to compute a transition between one state phi and one state psi in a pentagon with r units of our charge, all you have to do is to use the bosonic one and dress it by some simple function. So, that's what's written here. So you only have to dress the bosonic to get the charged pentagons, and then we checked. Then we did this perturbative check against the available data, and we found a very nice match. So this probe by one side this map that I proposed, but also all the ingredients of the pentagon approach. And so we believe that we have all the ingredients to, or we believe we can now compute any polygon for any helicity. But there's one ingredient missing that I'm going to talk about. So let me jump for the conclusions. So I gave you a concrete way of computing some n-sided polygon for any helicity amplitude in a non-perturbative way, and this is checked against data. But there's something to be done yet. So there is still the missing ingredient, which is this matrix part, which takes care of all our charge indices that you have in the pentagons. So there's some group theoretical part that is completely factorized and totally independent. And this is in progress and should appear very soon, but there were already some particular cases that were studied. Then, of course, there's once we have a result, there are things that one has to study. So, well, there's a big problem, which is not a big problem, the big open problem to be studied, which is to try to reason this obesity. Okay, we still have to do this some overall states, but eventually they might be able to reason them. And then to study the connection between these and other approaches. So the OP breaks some symmetries or makes some symmetries less manifest, like cyclicity. And so it would be interesting to connect these with other approaches. And finally, since we have a non-perturbative formulation, it would be interesting to go
what is the data? It's one group, two, how many groups, and maybe some readings are at all.
Well, we tested to one group, mostly entry level, and well, basically, we don't have higher group data much higher group data to study. To operate with structure. But entry level and one group pretty much we tested everything.
So you mean basically this the composition functions in some case in the
Sorry?
I mean, we test the composition functions. It's very simple. It's like one partly propagation.
Well, you can compute from multi-particles, but they factorize. So basically, all we need is to know the single particle position of one particle. And then from that, I don't know if that's what you're asking.
I see more questions, so let's back for people as well. Our next speaker is Shota Komatsu, who will speak on the uses of SOE.
Okay, so first of all, I'd like to thank the organizers for giving me an opportunity to talk. And today I would like to talk about our recent attempt to use the separation of variables for computing three-point functions at recoupling. And that talk will be based on this paper, which is in collaboration with Yufan and Jian and so. And and also I will talk about these two related papers. So the goal is, as I said, to apply this dynamic separation of variables to three-point functions of n equals 4 centimeters. I will explain what dynamic separation of variable is, but today I will basically focus on the recoupling. So that recoupling. And there are basically two motivations why we would like to study the separation. We use the separation variables to study this three-point functions. And the one reason is its relation to the hexagon form factor approach. So recently there was a proposal of computing three-point functions at finite coupling by these guys, which is based on the hexagon form factor. And although it's kind of effective, because although the hexagon form factor basically gives you access to study the finite coupling three-point functions, but usually in the end we end up something like additions, which in general is quite bulky. So it will be very nice if you can convert this kind of bulky expression into some nice compact form, for example, like the integral. And this is actually what I would like to show. I would like to show today that using the separation variables, you can actually derive some kind of integral expression for three-point functions. Okay, so another motivation is that the relation to the quantum spectral work. In the quantum spectral, the quantum spectral curve approach uses P and Q functions, and it is believed that the P and Q functions are sort of a natural generalization of the wave functions in squaring separation variables to finite coupling. Of course, today I will only talk about recoupling. They will be very nice if you can make more precise connection with the quantum spectral curve, because that will give you the method to apply the very powerful quantum spectral curve approach to the three-point function. All right. So before delving into the details of the computation of the three-point functions, I'd like to remind what is dynamic separation of variables. So I think the basic idea comes from a kind of different way of characterizing the excited states. So if you consider quantum field theory or many-body physics, you describe the excited states by putting excitation on top of the vacuum state. So in that case, excited states are characterized by the rapidities or momenta and the number of excitations. And sometimes it also has some flavoritisms. But on the other hand, if you ask the same question to, for example, undergrad students, who just finished learning quantum mechanics, then he or she will say that in the quantum mechanics, the ground states has no zeros in the wave function, where the excited states have many zeros or no's in the wave function. So in this description, the excited states is described by the number and the position of the nodes of the wave function. So what's interesting is that integral spin chain is something in the middle. So it actually admits two different descriptions at the same time. So the quantum field theory-like picture actually gives you usual algebraic and coordinate data ansatz, where the excited states is obtained by putting a lot of Magellan excitation with rapidity m on top of the vacuum state. So on the other hand, the theme of my talk, which is square separation variables, gives you something like a quantum mechanical picture of the excited states. In square separation variables, you can construct what is called SOV basis. And then using the SOV basis, if you compute the overlap, if you compute the wave function in terms of the SOV basis, you get this kind of factorized wave function, where each factor is given by the polynomial, and the zeros of the polynomials are remarkably precisely given by the beta roots. So what's interesting is that beta roots are playing two different roles in these two pictures. In the first picture, beta roots are basically the rapidities of the excitation, whereas in the second picture, actually nodes or zeros of the wave function. And this Q function is also called faster polynomial. So the question is how to define this X. And actually, to characterize it, the method to define this X was actually already developed long ago by Squiani, and I would like to talk about SU2 case. So the idea is to first take the monogeny matrix, which is just the product of Bax operator, which is given by A, B, C, D. And in the spin chain, the operator is a polynomial with respect to U, where we use rapidity. So you can actually convert this expression into a kind of factorized form, and here, if you write it in this form, this xj hat is actually, and Squiani characterized this SOV state as a simultaneous eigenvector of all x hats, which is nothing but, well, which is equivalent to saying that this x is actually the eigenvector of B of u for any u.
It doesn't define x uniquely.
It doesn't define x uniquely. So is it? Of course, yeah, after permutation is yes, that's true. Not only. Maybe we can discuss later. Okay, so anyway, kind of eigenvector of B of u. And then if you compute the overlap with x and psi, where psi is the data state, you get this kind of polynomial expression. And now this xj is not the operator, but it's just the eigenvalue of this x hat. So it's a classical number. And then you can convert this polynomial into the product of Q function. Okay. So, but there is a small subtlety in this construction if you want to apply this technique to the periodic spin chain. Because in the periodic spin chain, the leading term of B of u with respect to the expansion with respect to u is given by S minus, which is actually nilpotent and non-diagonalizable. So in order to cure these subtleties, you need to introduce some kind of twists in the monogeny matrix. Well, you can introduce twists at both stands. Epsilon is cos epsilon minus sin epsilon sin epsilon, where epsilon is assumed to be very small. So the idea is to first introduce a twist in the monogeny matrix, and later remove the twist. Later take the epsilon goes to 0 limits at the end of the application. But of course you can introduce two different twists, but in my talk I would like to just keep one twist in order to simplify the discussion. So if you do introduce this twist, then A of U becomes this kind of operator, which is the linear combination of the original A and C, and D of U becomes the linear combination of the original B and D. And what's the important property of this B epsilon U, which is a twisted B, is that the epsilon U is the upspin vacuum is actually the eigenvector of the epsilon U, and the eigenvalue is given by this. So this will be important in the later in the explanation. So this is the way kind of to use the machinery which was developed by Sklyanin. But actually, Sklyanin didn't tell the explicit construction of X. He somehow indirectly characterized this state X. But actually, you can actually very explicitly express this state X. And this was actually done for anti-periodic case by Niccoli, and for a more general boundary condition we did in our paper. So let's see how to construct this X. So the idea is what you need to do first is to first introduce the inhomogeneity, which is just a shift of the rapidity, and then the property I just mentioned becomes like this. So now the after spin vacuum is again of the epsilon, but eigenvalue is slightly modified. And you can, as you can easily see from this, if you set the value of the rapidity to be zeta j plus I over 2, you can easily see that this operator annihilates that spin vacuum. And this is actually an important property in the next slide. So the claim is that you can construct this X space by taking an arbitrary subset of alpha, which is a subset of 1 to L. And then if you consider this kind of state, it actually gives you the SOV state. So, well, first of all, you can immediately see there are actually, you can construct 2 to L state, which is consistent with the degree of freedom of the C2 spin chain. And the eigenvalue of X is given by these values. So for when J belongs to alpha, the eigenvalue of Xj is given by zeta j minus I over 2, and when J belongs to the component of alpha, the eigenvalue is given by zeta j plus I over 2. So now I stated the claim, so I need to prove this. So in order to prove this, it's actually very simple. Actually, the proof simply follows from the Maxwell algebra. So what I need to prove is that this state is the eigenstate. So what you need to do is to pass through this d epsilon, this d epsilons through all these a epsilons. So in order to do that, you just need to use the Maxwell algebra, which is given by this kind of expression. But as I said, since upspin vacuum, well, then you get two different terms. One is just the exchange of the operator, and the other is the exchange of the operator and the exchange of the rapidities. But as I said, this upspin vacuum is annihilated by zeta d epsilon of zeta j plus I over 2. You can actually discard this second term. So you can simply pass this d epsilon through all a epsilons. This state is actually proportional to the original state, which means that this state is eigenvector of the epsilon. So using this kind of explicit which is given by this. This looks like a matrix model integral, but what's interesting is that here the van der Waals factor is a kind of combination of the ordinary van der Waals and exponential van der Waals. So it's kind of something in between a neat matrix model, and you can see this as a potential term. And this Q of U is basically comes from the wave function, which is given by X and U. Another application, which is especially important for computing three-point function, of the SLP basis. So suppose we have a kind of SLP basis of one spin change, which is given by this form, and then you can consider what happens if you cut the spin chain into two. So after cutting, you can define the spin chain for the SLP state for the subchain by using the same formula, and also for the right spin chain, you can define the SLP states. And where this A epsilon and A epsilon left and A epsilon right is related to the original ABC expression. You just need to multiply left and right overlap of the origin basis and the SOP basis for the subchain. This quantity is of interest because whenever you do this computation at pre-coupling, whenever you do the computation of frequent function at pre-coupling, you spin chain into two. And also, in the hexagon approach, you need to split the spin chain into two. So this will be interest. This is of interest in that sense. So using the exclusive expression, you can actually compute this guy, and the result is given by a product of two factors. And the first factor is that is the factor which depends on the twist you introduce by hand. But what's more interesting and more important is this gamma factor, and this gamma factor is given by this kind of expression. And here, zeta1 is in homogeneity for the left subchain, and zeta2 is in homogeneity for the right subchain. And the result is given by a bunch of gamma functions. And here I'm using a simplified notation where the function with sets as arguments is actually the product of the function with sets, product over all elements of the sets. And here a plus minus basically means the shift by plus or minus I over 2. So let me just explain a little bit about the derivation of this. So to derive this object, we first need to compute this object where the epsilon is the p over the full chain is inserted in between these two states. Then you can compute this object by first applying b operator to x. Then, since x diagonalizes b, you get this kind of expression. On the other hand, this full b operator can be expressed as the sum of products of a and b operators for the left and right subchain. And so you can compute this quantity alternatively by first expressing this as this, and then applying this a left and b right and b left and b right to these ket states. So, then if you equate the two expressions obtained by these two different methods, you actually end up with some difference equation. And if you have difference equation and the initial data actually can be computed using the explicit expression of this SOP state in terms of A operators. And how much time do you have? 11 minutes. Okay, so then I would like to talk now about the application of the SOP method to frequent function. So the frequent function I would like we studied is this kind of frequent function, which also showed up in Pedro's talk. So the operator O1 is made up of Z and Y, and the operator O2 is made up of Z bar and Y bar, whereas the operator O3 is kind of a rotated state where the vacuum is given by this linear combination and excitation is given by this linear combination. So let me just comment about this frequent function at pre-coupling. You can of course considering that localized Covello from December Vieira, but that leads to actually very complicated expression. But there is some kind of refinement of the tailoring method. So-called singlet overlap of the spin vertex. The idea is to express this frequent function as the overlap of the three spin chain states and some what is called vertex states. This approach is very much inspired by the string P theory. And here R1 and R2 and R3 are basically the rotation you need. As I said, to describe the operator O3, you need to perform the rotation. And this R1, R2, R3 actually takes into account the rotation. And then if you use this kind of approach, you can actually exploit this material of the problem much more in detail. Then you end up with this kind of sum over partition expression where the sum is given by the product of three determinants, where this is called the serving determinant. But this, as you can see, this is still a bit complicated, I would say. And you can also using the hexagon approach, but in order to do that, you need to plug all the excitation to one edge by crossing transformation. And after crossing, the computation boils down to the computation of S matrix. But since some of the rapidities have crossed, some of the excitations have crossed rapidities, actually there is a fermion production already at the leading order. So because of this fermion production, actually what the result you get seems to be it would be nice to have yet another expression which might be simple. So the idea is very simple. The idea of applying SOP is very simple. Start this expression and insert resolution by identity here. Then you get this kind of expression. But there is a little bit problem here because, as I said, in order to use SOP, you need to use your hand and eliminate it at the end of the notation. But if you compute this guy, you get something like epsilon 1 over epsilon 2, which is where epsilon 1 and epsilon 2 are both split. So taking the epsilon goes to 0 limit is very much subtle. However, there is actually kind of a way out, which is to map the problem to the 6-vertex model and rotate by 90 degrees. So let me explain what I mean by rotate by 90 degrees. So configuration, the original three-point function configuration can be actually mapped to this 6-vertex model partition function, where this gradient line accounts for R, rotation, and this black lines are actually auxiliary space, and these blue lines are quantum space. And if you take this off, this shaded region, well, one good thing about this 6-vertex model is that it releases some kind of hidden symmetry of the problem. So if you take this shaded region and do some, rotate this left part by 90 degrees clockwise and the right part by 90 degrees counterclockwise, and you do the same thing for all the other two parts, you get this kind of figure in which the auxiliary space and quantum space are exchanged. So what's nice is that the R1, the original rotation, actually plays the role of the twist. So after this manipulation, actually the rotation becomes the twist, so you do not introduce the twist by hand. You don't need to introduce the twist by hand. And then you can actually easily insert this resolution by identity for the original SOP cases, and here you can insert the resolution by identity or identity of the subchain and get the expression, integral expression. And the final result is given by this formula. So this is the splitting factor, and this is the wave function factor, and the measure is this given by this kind of expression. And this TD1, TD3 are the rotation angle, which I will next right, but the most important part is given by this. So what's interesting, what's nice about this expression is that the rapidity enters only through the absolute polynomial or Q functions. So, and also another thing to mention is that when you take the residue, it actually reproduces the sum over partition expression. So this is the basically main results. Yes. Now I'm going to summarize in prospect. So what we did is to derive this explicit expression of the SOP cases for SU2 sector with the general twists. And also we derive the splitting factor in the SOP cases. And then we derive integral expression for tree-level SU2 three-point function. So, but as you can see, the expression is unfortunately still a little bit complicated. So it would be very nice to understand, to find a better way to write the expression. But in any case, this kind of splitting factor we hope that this splitting factor we determine will somehow in the future exploration. So, and another future problem is to study, for example, higher loop and other sectors. For example, for SL2, there is a nice paper by Solpo, but as far as I understand, this expression actually includes some combinatorial manipulation, so it's not entirely given by the integral. So it would be nice to kind of convert everything into the integral.
Sorry, does that mean it's an integral? But if you take the bottom, it will be combinatorial, but it's supposed to work.
Okay, I see. Okay, so, all right, thanks for the comments. Okay. So there is a paper by Jenny. And also, it would be nice to kind of express hexagon in the SOP cases. And another thing to study is the 90-degree rotation we used. It is interesting to study if the 90-degree rotation we used can be applied for other sectors, for example, SL2. And also, interesting if there is any relation to the mirror rotation, mirror transformation, which is heavily used in the S matrix, Lorentz S matrix, of course. So, and that's all. Thank you very much.
Thank you for a very nice, quick talk. So we have plenty of time for questions.
So just in the beginning, you commented the hexagon is very nice. just as too complicated, but I thought actually there was another problem that the data roots which are there at the size in positive, so you have like full correction there. The data roots which ampersand to the permutations. Those are, I guess, less than 30 people.
Yes.
They will get the corrections.
Yes.
So that's another problem.
Yeah, that's another problem. That's indeed another problem. Yeah. So here we are using, we are first rotate the picture, and then the homogeneity is played by the rapidities. The rapidity we are using is technical. That's what we say.
No, not in this pandemic.
Well, okay. Yeah, that's true. That's another thing. Yeah. Thanks for the context. Excellent. Yes.
So you say that Q has knowledge of wave function in this way. So, but divides them is this product of A the wave functions. So when you wrote IGST of XXX chain in this very basis, it was product of L Qs at the very beginning. So it's like product of L wave functions. But like from the point of view of quantum mechanics, I would say that not L exists. I mean, if you have one particle, it should be one wave function with a product of L of them. So a little bit felt of these other analogies.
Okay. The product of any. So you have a question?
Yeah, don't take the hydrogen atom and wave function is product.
Take one-dimensional quantum.
Well, take three-dimensional quantum mechanics. It will be a product of spin chain and it has L degrees of freedom.
What is the current situation with higher rank sectors like SU3? Could you the difficulty? I know that it's
so,
more difficult.
in my understanding, well, there is actually a general scheme to construct SOP basis in higher rank. There is a, well,
By whom?
there is a paper by Soriani for SU3 and Smirnov for SU11.
No, they say.
Well, I think there is one very.
So actually, there is a way to make it work, but I'm not going to comment further.
Yeah, but anyway, so what they are saying is it doesn't work for if you take, for example, you know, in the periodic spin chain, you need to modify many.
Nico Lee and these guys, they failed totally in higher rank.
That's the comments. Okay.
Can you show the results? So, in the usual formula, there is some addition of generating left and right.
Yes.
This result does not have any such summation. Why is it?
Well, actually, all the sum over partition are sum converted. So if you take the residue, it produces sum over partition. That's how it works. For example, well, it's a little bit hard to see, but as you can see from here, there is a pole at U plus I2 and U minus I2. And depending on which pole you take, actually generates.
More comments or questions?
Yeah.
I see none, so let's thank our speaker. So, Florian tells me he found a mobile phone. Samsung. Is anybody listening on a mobile phone?
speaker of this conference is Tomek Bukowski from Oxford, who will speak on large spin systematics in CFD.
And I'd like to start by being an organizer for the gathering here and give me an opportunity to speak about my work together with Randall Dye and Anessa VC blog in Oxford. And it's all the talk is based on this one paper which we published a few months ago. And unlike most of the talks at this conference, I have a bit different motivation to start with. And I'll come to integrality at some point in my talk, but my basic motivation comes from this parallel development, which is the conformal bootstrap, which in the last almost 10 years now is trying to some new methods for solving conformal field theories in dimension bigger than 2. And even though the methods of integrability in the conformal bootstrap approach are different, then the basic idea is very alike. We have some symmetry of the model. We would like to use the symmetry in order to bootstrap our answer. And unlike in integrability or this infinite dimensional algebra, here what we'd like to use is a conformal symmetry together with symmetry, unitarity, and the structure of the LPE. So there's much less than we have in the integrability, so the results will be strong. But it will apply to much larger class of models. So there's more models, more conformal models in dimension bigger than 2 than integrabilities. What I would focus here in this talk on is a particular class of operators in this generic conformal theory. These are operators with large spin. And to simplify the discussion in this talk, I will not focus on dimensional theories, and I will also focus on very particular operators where we have. So these are operators with large spin, but the case with some scalar. And what we like to study, we like to study these operators, study their conformal dimensions, and study the frequent couplings. So for people working in integrability, these operators are very familiar to. The twist operators are of this form, and we know that this is exactly the operators for which the integrability methods were used. These operators are exactly the same structure constant with Pedro mentioned very end of the talk. So the results which I present here will be exactly for this class of structure constants. So in general, why these operators are interesting is not only in conformal field theory, but in general field theory is the leading twist sector of these theories, which means that these are the first object the simplest object we like to study. And for example, in QCD, they are related to, that are present in the study of inelastic scattering. And as we already heard today already, the large spin, so these operators with large spin are related to some divergences of the Wilson with cut, and also to some divergences of the scattering. And as I mentioned, they are also very important for the integrability in ADC. And I will constrain myself even more. So first, the results which I present here are valid for perturbative calculations and for non-perturbative calculations. But in order to show you how it really works, I will focus on perturbative. So I focus on gauge theory. So I take some gauge theory in 4 dimensions, and I study these operators. Now I have some fields transforming adjoint of the gauge group, so I take trace. And it's known that in this case, these operators at large spin, they increase. So the dimension minus the spin behaves logarithmically with the spin. It's a universal behavior independent of the coupling constant. So there's some function of the coupling constant in front of this block behavior. And this function here is the one which Hannes mentioned. This is the light-like version of it. So in this particular limit we consider. So this is just the Campbell dimensions which appears in many places, like it's counting that because in use on 2 classes. And the question which we'd like to ask is the following. So this is the linear behavior. Can we say something about the structure for this? And the answer is no. And the answer is given by the so-called reciprocity principle. So the answer is the following. If I introduce the auxiliary function f of f here, which is defined by this formula in bracket here, in the box, just a twist minus the classical dimension. So it's a classical dimension minus the spin. If I define this function and I expand it as a function of L in large L, then it turns out this function is not a generic function, but it can be written using only even powers, even inverse powers of the quantity J0 here, which is just L times L plus 1, which is just the quadratic Casimir of the collinear subgroup of the conformal algebra at period. So what this formula means here, it means that if I treat it as a function of L, I should have all terms in the expansion, but even terms or all terms will be written as of even or vice versa. So this restricts the structure of the answer, and whatever answer you give me, you tell me that this is a conformal dimension of some operators in the conformal field theory. I can check it if this does not hold, then your answer is wrong. Okay. This reciprocity principle was first observed in QCD, so not even in conformal field theory. I come back to this later, but then later it was generalized also to many other theories, and it was scored, was checked in very many. But unfortunately, the proof was still missing. So it was just an observation based on the data people had, but unfortunately, the proof was not known. So in this talk, I provided proof, and a similar statement which was not known before. Okay, but in order to proceed, I will reformulate this reciprocity principle, which usually is written as that, but there is a simpler way of phrasing it, is the following. So instead of considering this J0, which is product Casimir at the tree level, I will take the full of at any coupling. And in that case, this statement here, these two statements here, can be rewritten as the fact that the anomalous dimensional can be written as the function containing only even inverse powers of J, output is not in front, in this J, which is the full Casimir.
Sorry, can I just ask?
Yes.
When you say that proof is missing, a proof is missing for any theory?
There is no proof, it's just an observation. I think that this, like I tell you now, is the unproved German. In any theory.
Can you just remind me what Benjamin and IGST15
They checked this property for many, for many theories, for QCD, for many anomalous dimensions, but there is no proof. I will prove this just directly from the properties of conformal theories and the properties of LP.
I actually comment just the reason that I was trying to understand the meaning of it. And actually, in terms of one spectral surface, just one for the exchange in like Q1 and Q2. So if we change some codings, that's what it is. So this property is another. So you can prove it.
So I give the proof here for generic CFT. So and then the log square. Yeah. So this A's here, these are polynomials. So sorry, I should say that these are polynomials without there can be any power. The power is usually very small here, like the second log square, but it can be. Yeah, so this is a polynomial in log, so it has a 3 term plus log J plus. So
If I just say that would become log J.
but it could depend also as a powers in J.
This is it.
So
So the main message is even part.
yeah, the main message is even parts, which means that there are zeros here, which could be there. If you take the generic function and we do this expansion, you will see that it has generic functions, generic expansion also in even parts. Okay, so this is the step which I'd like to prove for you, just starting from principles of conformal theories, in 4 dimensions to simplify that. But before I do that, I just remind you the fact which you know very well. So if you have a conformal field theory,
then the conformal symmetry restricts all the correlation functions. So two-point, three-point correlation functions. The space and dependence is completely fixed up to the right-hand side, as I wrote here. And the only thing which is not fixed by symmetry is the conformal dimensions and the trivial count. And additionally, we can also write as in field theory operator product expansion, and the particular, so for conformal field theories, the fact is that this constant which appears here in the LP is exactly the same constant as the one which appears in the operators. And just using these two facts, we can combine them together. We can take any point correlator, and we can just use PE, and then we use this CFT tech. And in principle, if you're powerful enough, you can find any number of points, so correlators of any number of operators. But here in this talk, I will regard this in general bootstrap. It reverses the logic, so we don't start from 3-point functions, we start from higher point functions. And we try to use a consistency condition for higher point functions in order to bootstrap this object, so to bootstrap the dimensions and structure constants. So the first non-trivial example is a 4-point correlator. In this case, the space-time dependence is not fixed completely, it's fixed up to a function of two cross ratios. And then if I just take this function and I use the OP twice, so I take the point 1 and 2 close to each other and 3 and 4 close to each other, then this 4-point function decomposes into the sum, where the sum goes over all conformal primary operators, all conformal multiplets which propagate in the intermediate channel. So this is a sum over some conformal dimensions. So each conformal primary is specified the conformal dimension and spin, and I have to just sum over all of them, and also include the identical operators as an external states. And this function G is just a conformal block which sums all the contributions for the descendants for a given primary. Okay? And usually what people do in this conformal bootstrap business is that they are taking this OP expansion, and one can take another OP expansion and take 1, 4, and 2, 3 close to each other, and these two expansions should agree with each other, and you can write so-called conformal bootstrap equation, which then you can try to use it to find some numerical for the CFT data. I will not go to this equation. In this talk, I will just focus purely on the fact that the 4-point function can be expanded in OPE, can be expanded in the conformal blocks. And I'll just focus on one channel. So let's say I'll just focus on the channel where I get 1, 2, and 3, 4 close to each other. Okay. So before I tell you how to prove the statement of reciprocity, two very basic properties of the conformal blocks are the following. So as I told you, the operators which are linkers mean are the leading list operators in our. And the conformal blocks, if you just write, so in 4 dimensions they form this completely known, and if you just expand it in leading U, so one of these cross ratios, in the sense that the power is governed by the twist. So in order to study the lowest twist, you just have to expand the leading order in the U, in the U expansion. So in that case, the conformal block is just this power tensor function, which is purely a function of phi, of the second cross ratio. And this function is just some hypergeometric function, so not also difficult function. And the second property which we use is the following: that this conformal block in this limit is just an eigenvector of some differential operator, where the eigenvalue is exactly the same quadratic Casimir which I use in this expansion of the anomalous dimension in the reciprocity. So this is two facts we use. Okay, so let's do that. So let's take this equation here and just focus on the leading twist operators, which means we expand the leading indicator. And as a first step, I just split the discussion in 2 steps. One step just focus purely on 3 level, and then we go to perturbation here. So at 3 level, the 4-point correlator is very easy, and this leading U behavior is just given by this 1 over V plus 1. And this has to be decomposed into conformal blocks where now everything simply because we are just focusing on the leading twist contributions. Where I put all, so we have 3 levels, I put all the levels dimension to 0 and all the treatment cavities to 3 levels treatment cavities. And what we can do, I just take this equation and solve it, and one can find this all the structure constants at 3 level. They have some very simple form. But there's a very interesting property of the property is the following. So on the right hand side, you see that if v is close to 0, there is a divergence there. So the right hand side goes like 1 over v. But if you take a look on the left hand side, so the left hand side is this hypergeometric function, this hypergeometric function, where when v is close to 0, it's some polynomial times maybe some log terms. Okay, so it's just branch count there. So if v is equal to 0, this function has branch count. When you start to expand it in small v, it's just giving you log. So now, in order to find, in order to find this equality and this divergence on the right hand side, what you have to do, you have to resound all this. You have to find what's the reason. How is it possible that this log plus logs times polynomials will produce 1 over v? And the other way to do that is that you have to resound infinitely many logs, right? So you have infinitely many logs, and you resound them, and it turns out at the end that it's 1 over v. Okay, and this. So the first thing is that we just, we need really the sum to be infinite, and the second thing is that we can also remove from the sum. We can remove the first some finite number of terms, and still we'll be able to reproduce this 1 over v divergence, because this divergence that purely comes from the tail of this sum. Okay. And if you want to reverse the logic, if you know the right hand side, then it means that if you know the divergence of the right hand side, it means that the large L behavior of the A0 is completely fixed by the right hand side. So we can just I'll tell you in a second how to do this in practice, but we can just say we can expand this A0 in large L, and then the leading term will be completely fixed by 1 over v, by the divergence. Okay. For perturbation theory, everything gets corrected by some perturbative terms, and so your dimension gets corrected by some anomalous dimension. The structure constants I write with this very strange way where I just factor out the 3-level part, and the 4-point function also gets corrections in G. Now, this is proven that using the analyticity of the conformal blocks, that what will happen to this 1 over v plus 1, so to the 4-point function, is that it will change into some 1 over v times some function which purely depends on log u log p. There's no pure t or pure u dependence there. And the right hand side is written in terms of the integer powers of v. So it can be negative, but it's always integer powers of v. So this comes directly from the 3-level structure and from the analyticity of the conformal blocks. Now, what we would like to do now, we would like to take this 4-point function, which is some generic function in v log u and log v, and try to decompose it into conformal blocks. So try to write a sum of conformal blocks equal to this. Then we would like to study how we can obtain the divergence that we have here. So how to obtain, again, similar to the 3-level question, how to obtain this H0. So this divergence, again, will come from some sum over log terms on the left-hand side, and the important information we'll see in the region where L is log. So only the tail of this sum will be important for our discussion. Okay, so I have exposed it to some calculation now. It will be very short, but this is the real method which we use. This method is just 2 slides, and it's very easy to reproduce. Okay, so what do we do? We would like to say something about this conformal composition of the 4-point function in the perturbation theory. The right hand side is just 4-point function, the left again the sum of write it as some polynomials in log j plus polynomials of log j divided by j, and so on. So it's an expansion in 1 over j. And this j is again the second cousin of the polynomial conformal group. So as you said, we would like to focus on small v, and this means that we focus on large L. What we can do, and we focus on the sum. So it means that we can take some small v, rescale L, change sum to be an integral. Then we have also rescale z is an integral. We have to rescale the Casimir operator.
Can I ask something?
Yes.
So why couldn't you have, for example, log square over j?
Log square over j. Sorry, this again, the P1 of log j means is a polynomial of log j.
Arbitrary power?
Oh, arbitrary power. Usually it's bounded from the power. But I think we don't assume this. It's arbitrary.
It can be polynomial of unit.
Yes. We don't assume that. Okay, so then what we do, we just take our arbitrary function, go to integral representation, make a subject bond, and this is what we get. So we get some divergence as we expect, so it's 1 over v, epsilon equal to v, times something. But then the strange thing is that we also get the term which is 1 over epsilon 1 half. Okay? Which was not present in the A. Plus some finite terms, but we don't have control over finite terms because we remove the finite number of terms in our sum, we just focus on the tail. So this approximation is good for divergent terms. So we don't have any control over. But if you now take a look at this expression, we like to compare it to right hand side, which is a four-point function, then you see that this integral here has to reproduce the same zero term, but there's no term here which looks like v2 minus 1 half. So it means that this integral here has to be equal to 0. But it turns out that for the class of functions we consider, which means that these are polynomials of log of j, so all these are polynomials of log of j, this integral transform has a 0 terminal, which means that if it's equal to 0, also the function here is equal to 0. Which means it doesn't and as a result, we get the P0 has to be equal to 0, and this combination here has to be equal to 0, which just means that this term here is 0, which is exactly what I said in the reciprocity principle is telling you. But also we get something extra, so what we get that the Q1, which is the expansion of the trigonometric coupling, is related to the expansion of the anomalous dimension. Okay. So this is something which we didn't expect at the beginning. Okay, so this first term now we don't have any control over the finite term, but there is a trick. And you can perform the following trick to also get access to higher terms in this expansion here. So to P2, P3, and so on. In order to do that, before the conformal blocks are eigenvectors of some differential operator. You can take this differential operator back on the left-hand side and the right-hand side. On the left-hand side, it is just produce for us this j squared over epsilon, which just increase our divergence. And we will not change the identity. We end up again with some function which is only integer powers of v. And then we can do this many times, and we can reproduce our logic, and we have access to more and more terms because there will be more and more divergent terms. So they will see more and more of this expansion. Okay. So this gives us new construct. The answer is the following. So if you just do this up to some order, then you get the answer, and the answer is the following. So the first statement is exactly the same as we knew before, so that the anomalous dimension can be, it's possible to write it only in terms of the even powers of 1 over j. The second statement is completely new, and it was not known before. And it's the fact that this rescaled trigonometric coupling divided by this strange combination 2 plus gamma prime, it's also expanded in large term, and the expansion will contain only even parts of 1 over j. So this gives a new restrictions for structure constants. So this result calls for negative order. We didn't assume any anything about the perturbation theory and we didn't say anything about the form of this functions, which we consider apart from the fact that they are there are some functions of and it also in arbitrary dimensions since the conformal block is exactly the same for the leading part of the conformal block is exactly the same in any dimension. It also holds for you can take other operators and apply the same logic to them and you find the same answer. Okay, so one can check it, for example, for input 4 up to 6 loops in gamma and up to 3 loops which are known at the moment for A. And this result is non-planar. I mean, we did planarity. So one can check it in the planar sector, but the full non-planar answer also satisfies the same conditions. Now,
and linearly, if you follow the operator, the dimension will not grow logarithmically.
sorry.
If you follow the dimension and linearly,
Yeah.
and planar, at some point levels will cross.
Yeah,
And
yeah.
your operator will go to a product of two double traces, and instead of growing logarithmically, the dimension will decay to our level.
Yeah. So, but I'm talking about really small g. It's really perturbation theory when you're really in the region before you cross. There's a region before you cross, which is it's the expansion 1 over n. So this can be generalized to non-perturbative CFTs, and the statement is very similar. So this is exactly the statement usual. So non-perturbativity, the statement is that there's a power law here, but the subleading terms they organize in the same way. So there's no odd there are no odd powers of the Casimir here. Okay, and the same, and then there's based on very similar techniques. It was shown by Fernando and Sasha that it also can be generalized to non-conformal theories, and when you simplify that there exists a dimension in which for which the beta function is equal to 0, and you can use and since the conformal blocks for the leading twists are independent of the dimension, you can use the same logic and prove that all the anomalous dimensions will be can be written on in even powers of the Casimir, where now Casimir also depends on the beta function of the given mirror. So this is a statement that was known in QCD before we in 87, right? Okay. To conclude, so we derived an infinite number of constraints on the large spin expressions for operators which have this large spin. And there was a known fact for anomalous dimension which we just proved here, and also extended to non-perturbative theories. And we have new reciprocity principle for OPE coefficients. And now you will ask how can we use it. For example, we know if Pedro and collaborators they want to go to some higher loops where there's no way to compare their result with any standard methods. Then the only thing which we can do is to try to produce some consistency checks for the result. And this exactly is one of the consistency checks. So whatever result you get, one has to check if this result satisfies this constraint which we proved here. Okay, so what are the future directions? So this is what I said already, that just a bit simple for the OPE coefficient in order to predict something about structural constants. We used only the fact to get real numbers, not only the restrictions on the structure of the answer. Further in the video expansion to some subleading twists. And can we check also the second constraint on the OPE coefficients? Is there any way to use this information in QCD where there are Wilson coefficients, and can we say something about Wilson coefficients using this?
So, how do you distinguish between perturbative and non-perturbative and the non-perturbative case? So, is it true, for example, that you are always assuming that the leading behavior is with a spin, which is true for some gauge theory or gauge theories?
No. So we really have to distinguish these two cases. So in perturbation theory,
Is it in a generic CFT? That's not true.
So it's only for gauge theories, as far as I know. And I think that is in this paper. In this paper, I think that there is some alternative for this statement also. So for non-perturbative theories, the indicator will be the other one. It will be this indicator. But our argument works in both cases. Okay. So you cannot go smoothly from one to the other because I mean, this would be assuming that non-perturbative region is the fact that there is some least gap between states and between the operators. And
Sorry, what is the assumption again?
in non-perturbative theories, we have to assume that there is some gap between, I mean, the thesis gap from protecting the zero.
But why isn't it going in the perturbative case as well?
I mean, in a sense that if you take G to 0, then there's no gap.
Why? Why does it not? You cannot have operators with dimension 0.
I mean, there's infinity many operators with this scope, right? And at 3 level, there's these operators that have all this scope, right? That's for all that.
Is there another question? Come ahead.
Is there some analog of reciprocity relation, say, when you're in the regime of perturbations here around BFK, right, and delta?
No, as far as I know, there's no.
That should be very similar because those extensions are almost the same, right? Just replace that by. Should be some simple analog of this.
So maybe there is some.
Which would help a lot.
Yeah.
Okay. I don't see any more hands, so let's take Tomek once more. So, now we come to the closing part of this marvelous conference, and we now have a very special event, which is due to gases, which of course plays an important role in our meeting, financing at least my trip and many other things. So we have the famous awards, which will be, I'm not sure who's, I think there's still some discussions going on. So there's best lecture at the Iris School, which took place last week in Durham. To my knowledge, that prize is already known. And then there's a best prize for the scientific paper written last year in our area of gauge theory and integral systems. Strain gauge theory and integral systems. And finally, there's also an IGST15 presentation award, and everybody qualifies, also Tomek, the last speaker. So that's why I think there had to be some final discussions, which seem to be ready, so I hand over to Volker.
Okay, thank you. I didn't really listen to what Jan said. No. We had many problems. I mean, we should have music for the ceremony anyway. I heard Sergey wants to sing, maybe. Yeah. There's no way. Okay, so I'm lucky. Okay, so yeah, so we're not fully prepared. Also, Christine, the manager of campus, had to leave just before this, so I was hoping I would get a little bit of assistance, but we'll see how it works. So when we wrote the description of work for GATTIS like many years ago, we had this idea to introduce a few awards, and now we finally managed after 2.5 years to implement that. And so you're witnessing the first ever award ceremony of candidates. Please keep that in mind. Okay, so as Jan, I think, told you in the beginning, there's 3 awards, and the first award is actually the awardee is in fact known to many of you already, because that concerned the best lecture at a school that was we had in Durham last week. It was actually organized by young fellows, and the teachers were young, non-tenured lecturers, and the audience voted for the best lecturer. And the result of that voting will now be announced to you by Alessandra Cagnazzo, who was one of the organizers of that school.
So all the speakers did an excellent job during the school, and this is remarkable because they are young and they don't have much teaching experience. But the young participant to the school decided to award the best lecturer at Young Researcher Integrability School to Alessandro Torrielli.
So, this being an award ceremony, there has to be an envelope. So actually, the jury met. We discussed via email, and after many heated discussions, we actually decided there would be 2 winners this year. And I don't know how the money will be divided up. That's up to you. So let me announce the winners. The winners are first, John Toledo for Smooth Wilson Loops from the Continuum Limit of No Polygons. And the second is actually a collaboration. I don't know if you do the prize. Oh, okay. Well, I'll announce all the authors. Okay. The second is for Ricardo Bossato, Olaf Wilson-Sachs, Alessandro Spandrini, and Bogdan Stefanski towards the all-blue worldsheet S matrix for ADS3, cos S3, cos T4. So Alessandro is the ESR, so please come up. Just like to say that we had many excellent papers. It was a very hard decision, but well, somebody had to win. They're buying drinks at the pub tonight.
Okay, thank you. Oh, we took the envelope again, so let's do the last one without it, we have an envelope itself. Okay, so the last award is the IGST presentation award, and this is a logistic challenge, as you can imagine, because IGST just is. And so here the supervisory board, so basically eligible are, I should say, talks by people that have completed their PhD no longer than 5 years ago and should not have a tenured or tenure track position in the faculty. So, and here the supervisory board makes a decision. In this case, was actually the decision was assisted by two speakers who you saw also during this week and gave an excellent presentation themselves. It was Bogdan Stefanski and Dima Volin helped discussing this award, and I think Dima will now announce the decision.
Yes, so as Zeros class said, the class includes all afternoon speakers. It actually was quite tough to decide who will be the winner, but it should be one. So we agreed on Eli Komani.
This time we didn't have time to put the name in. Because it was really was open until the very last minute. So yeah, let me use the opportunity to say that this was really very tough, and I think especially these young lecturer, young participants talks were really quite excellent, and I think we had very tough discussions about what to do. What?
Was the best
The best Okay, so that brings me to the end of this award ceremony. Again, next year maybe with music. And I should say all the awardees should come back after, because there's, of course, the prize still here, and I need a signature in return. This is the EU bureaucracy, of course. I mean, I cannot just give you money without signature. Okay, so I hand back to Jan.
So there's more to come. So I would like to use the opportunity of this closing to draw your attention to a number of related meetings which will take place next year. And the first one is to remind you of the workshop at Nodita that was, as I already announced, will take place in April for 3 weeks. And is devoted to some, a little bit wider set of subjects, but also to gauge spirituality's particularity. Then there will be a PhD student and young postdoc school at Bezouche, which is a marvelous place in the French Alps. I can tell you, as I was there as a PhD student as well many years ago. And it will take in June. And we have, well, the organizers are up there. Particularly Dina is, as far as I understand, in charge of it. And there's a number of long-term lectures and shorter-term lectures. I think only I will only give one lecture.
He's got two solutions.
But it's such a tough problem, so in any case. So I think this is this will be very interesting. I don't know when the will be open. Is that already open?
Probably September. By September we hope to have the website.
Okay. So by September there should be a website and the possibility to apply. Great. And then, last but not least, I want to announce a very large, 3-week program that we're going to be holding in Berlin, which runs under the name of a Customers Summer University, and that's due to the this is a concept at a university to fund such events in the framework of Excellency Initiative, and we were lucky enough to acquire that money, so we will have a 3-week program altogether. Starting in mid-August and running till end of August and beginning of September. It will start out with an edition of the well-established and enormously successful, I think, Mathematica schools, which will be organized by Finn Vienna and Tonya Gromov. In the first week, the second week will then be the IGST15 conference, which we will hold in Berlin at the so close to our institute. And finally, there will be a third week focus program or workshop style, where we will be able to discuss the exciting new results that have been communicated at the IGST. So note the dates in your calendar, and we will also go online in the near future, I would say. Good. And that brings me to the end. And I think that this is, we all should extend huge big thanks to the organizers of this IGST 2015, which I think was very well organized in a very nice location, great city, and I think we had also a marvelous dinner yesterday evening, which is very memorable, and which puts a lot of pressure on us from the Berlin side to at least match what we could experience here. So let's give a big thanks to Nadav, Kolya, Akadi, June, Jao, Theodore, and Christian.